And after that, our guest speaker, Chris, is going to talk about the science of Star Wars and all those lovely films that we see. Really looking forward to that. At the end of that, there will be an opportunity to ask questions. So if you could wait to the end of the talk, you can then ask your questions. And then I'll follow up with a few other announcements, not very many, and then we'll let you go. I'm going to say a very special welcome to those of you on Zoom. It's lovely to see you too. I know we've got people as far away as Bradford signed up. So, it's really nice to see you joining us, and the wonders of Zoom allow us to do that. For those of you on Zoom, if I can ask you to keep your hands away from the space bar so that you stay muted through the meeting. And if you have any questions, you can submit them via the chat facility. For those of us in the university, the toilets are just outside the door there. And can we ask if you've got mobile phones that you can set them to silent or turn them off? Also, that we're not expecting to practice the fire alarm this evening, so if it does go off, please go through the exits as marked and assemble on the car park, where we will check that everybody is safe and sound. I'll just have a quick look at my notes, make sure I've got everything covered. I just wanted to say the last meeting we had to finish it rather quickly because of the time constraint. Some people sent questions along about Jerry's talk, and they are published on the website. If you go on the main page, front page, there's a link there to the questions and the answers. So if you can avail yourself of that, that would be really good. Similarly, we've had a letter from Simeon, who gave the first part of the talk, which was about blinded by the light. I was talking to Simeon this afternoon, who was talking about the next step, and he said, would I be able to publish a letter to the members? I said, if you get it to me quickly, I'll get it out tonight. So just a quick read, it's not a very long one. It says, hi Alan, thanks for this, my email to club members. Right, dear citizen scientist members of the Hertford Astronomy Group, thanks so much for your attention the other night. I hope some of you found Blinded by the Light of interest. So this email is to ask each of you if you would like to be part of a brainstorming session, 7 o'clock to 9 o'clock on Wednesday the 22nd of May. That's 2 weeks today at the university, room to be confirmed. All ideas, no matter how apparently crazy or over the horizon, are most welcome at this stage. Of course, more pragmatic and practical ideas are also welcomed. I see this as an opportunity to flex our creative muscles, and I will kick off the evening with a 10-minute creative cognition exercise I use with my MA students. That helps to get things moving. I hope that hasn't frightened you off. If you want to go along to that, I'll send a message out to remind you about it and put a link in it, so that if you want to come along to that meeting, even if you just want to sit there quietly in the background and try and understand it a bit more, you'd be very welcome to come. Both of those talks we had last time are recorded and they are published on the website. So if you want to refresh your memories about them, go onto the website, the other links page, and you'll find at the bottom there's a picture of Jerry. Click on that and you get the whole meeting. There is a marker on it so that you'll know which bit Jerry starts at and where the other one starts at. So that's enough from me. I'm going to hand you over now to John, who's going to talk about the night sky.
Okay, I assume everyone can hear me. Whether they want to hear me is a different matter, but okay, brilliant. I've got to say, I forgot to bring my glasses today, so any facts or numbers I quote that aren't on the screen are very much needs citation. Okay, so I apologise if I've got any of this wrong, which I undoubtedly have. Okay, so I'll try to keep this to 10 minutes. I say that every month I do this, and I've never yet managed it. Okay, so Quickly with the moon, it's the usual phases, oddly enough. Tonight is new moon. Why are we all here? And we carry on through to 6th of June, new moon, which I think is about 4 days before the next meeting. So our meetings aren't timed for the best for that. We have a occultation, of Neptune this month. Sadly, you can only see it if you're in southern Africa, but we do get quite a close meeting of the moon and Neptune, and we'll come back to that. Okay, so Venus is out of the question. It's going to do solar conjunction on the 4th of June, so it'll be coming round again. Jupiter, you can just about see. It's really lost in the evening twilight, but it's on magnitude about -2, so it's very bright, so you might be able to see it, particularly if you know where to look. But you won't get anything out of it. It will be bleached out. So I'm saying it isn't there. There is another one that isn't there, but it's worth mentioning later. Okay, so Mercury and Uranus. As always, do not look at Mercury when the sun is visible. Incredibly dangerous. I know everyone knows that, but I always say it because somebody might be hearing this for the first time. Do not look at it through even naked eye once the sun is in the sky. Okay, so it gets its maximum angle from the sun on about the 10th of May at about 26.4 degrees, so that's your best chance to see it. And I can't actually see what I'm looking at now. Okay, so it's very low in the east of the sky and it's in Pisces. And you'll find that all the cool planets are hanging out around Pisces this month for some reason. They're all there. And you can see Mars off to one side. So it's going to travel across Pisces and it's going to move down towards Taurus. It's going to be it's going to be lower and lower in the sky as the month goes on. Now, Uranus is pretty much lost in the night sky. I haven't written down the magnitude and I can't remember it off the top of my head, but it's pretty high. It'd be 6 or 7. But you do get this nice conjunction. 1.3 degrees separates them. On the 31st of May, and that's just off Taurus. You can see the Pleiades over towards the left of them. Jupiter's down there, like I said. You might be able to see it, you won't be able to make out much. Very low in the sky, and this is happening just before the morning. I think morning. Okay, so Mars, it's been months since I've seen Mars. Mars is rising low in the east. Gets up at about 4 a.m, which is far earlier than me, and it's going to be getting up gradually earlier as the month goes on. Magnitude 1.1, which is pretty good. Another one hanging around at in Pisces. Did I say Pisces before? It is Pisces, I meant, yeah. So it is, it's going to be crossing that. Nice red star, 1.1. It's going to look quite nice and bright. The moon gets fairly close. Not easy to see on my drawings. I keep thinking I'm going to have to do better on this. But it gets reasonably close. Well worth a look. Saturn and Neptune. So they're both very low in the east. You can just see this, the E in the bottom left-hand corner is on the ground. They're just off the east. The moon gets within a third of a degree, about 20 arc minutes of Saturn at the end of the month at about 2 a.m. And Saturn's pretty bright, so that could be quite good. And then the next day, it jumps over here. Now, Neptune is 7.91. You cannot see it. But, well, you can't see it with the naked eye, I should say. You'll need a small scope, or binoculars might be able to get it, but it should be easier to find. So if you want the outermost planet, if you want to be able to see it, and I confess I've never seen it, it's an opportunity to see it on the 1st of June. Okay, and that's even closer the moon's going to be to Neptune. All right, so what happened last month? So this is just the news that I saw that interested me, and I'm not saying this is completely covered it. So I think it was last year they replaced the batteries on the ISS, and it was about 2,500 tons, 2,600 kilos. Got released in the atmosphere. The plan was it would all burn up in the atmosphere. Well, about 8 kilos, I think, failed to burn up. Went through some poor guy's house in Florida. Fortunately, didn't hurt anyone. And of course, it had to be Florida. So The Psyche mission, now I spoke about this I think in the January talk. It was about 19 million kilometres from Earth, and it did about 256 megabits per second data transmission with Earth, which is incredible. It can be a great problem getting the information back from probes, and it limits how much they can do. It took months for the data to get back from New Horizons. This is far faster. So they have done it 25 megabits per second at 140 million kilometres. So this is really encouraging. This is great. What is really frustrating for me personally about this is genuinely, and I'm not exaggerating, this is genuinely faster than the broadband I get at home. I've got terrible broadband, and I think I'm getting 22 megabits. It's terrible, and I don't seem to be able to get it any faster. But anyway, so Voyager 1's back online. Again, something I spoke about. It was out of action for about 2 months, just sending gibberish. So I think it was in the flight control data system, they found a third of the memory had been corrupted. And they reprogrammed it, and when you consider these are 40, 50-year-old computers, because they're not new when they went up, and they reprogrammed them, and they worked around it. In the limited memory they would have had, limited space. I was a programmer for about 40 years, and I am just in awe of what these guys can do. Absolutely brilliant. JAXA, spoke about JAXA as well. The slim lander, the one that landed on the moon, one of the legs collapsed and it went on its side. That is still working. That was actually built to survive 1 lunar night, a night being 2 weeks on the moon. This survived 3 and is still going. So a bit like the rovers on Mars, it's exceeding its design parameters, or probably its minimum success parameters, but it's encouraging. As I said last time, JAXA is one of those space agencies I never feel gets the credit it deserves. On the bad news side, Hubble has gyro issues again. So the last space shuttle mission to it put 6 new gyros in. They've gradually been failing. Normally it needs 3 to operate. It's down to 2. I don't know the one that just went offline they can fix. It sounds like it's a power issue. It's the flex cable that carries the power. They get corrupted or corroded, but they have a mechanism. They say they can align it with 2. They have a plan to align it with 2, which will also work with 1. NASA's saying Hubble will be up there we'll be delivering science into the 2030s, so let's hope so. Right, JADES. I can't remember what this acronym stands for, but the J is the JWST. And it's found population 3 stars, hopefully. I don't think it's been peer reviewed. Now, our sun is a population 1 star. The older stars are population 2, and the very first stars in the universe are population 3, which shows astronomers cannot name anything, should not be allowed to name anything. So these stars came out about 13.4, was seen for 13.4 billion years ago. They're about 400 million years after the Big Bang, and they have no metal in them, or the spectrum shows no metal because they only had helium, hydrogen, a tiny amount of lithium, and they have double ionized helium. What double ionized helium is, I'm not 100% sure, so please don't ask me. Tokyo, the University of Tokyo has put up a new telescope on the Atacama Desert. It's 5,600 meters above ground level. It's the highest on Earth. It is so high, and the sky is so dry up there, or the air is so dry. It's the only ground-based telescope that can do near and mid-infrared astronomy from the surface of the Earth. Sorry? Oh, sorry. Vera Rubin, which is the proper name for the Synoptic Sky Telescope, which has the biggest digital camera ever made. I forget how many gigapixels this thing contains, has had its primary mirror coated. This is going to map out the sky. This is going to revolutionise the sky. I think its first light, I can't remember if it's later this year or next year, but it's slowly coming together, and it's going to be a totally awesome telescope. It's one of the first of the new big breed of telescopes. Next month. Launch of a solar sail. I think the Planetary Society launched one in 2019. This is another one. I don't know how big it is. I couldn't find out how big it is, but it's going up in a CubeSat, which is only about the size of a shoebox. So It's not going to be that big, but they've got new struts, ways of unfolding the struts. This will change sending probes around the solar system. You don't need to launch the fuel if you can reflect the light back and use it very much like an old-fashioned sail. Starship. Hopefully we'll get another launch because they're entertaining even when they're not successful. Incredible when they're successful, more entertaining when they just blow up. I can't find a window. I did have a look to see if they had a window and they might launch it, but there hasn't been one. Okay, so I was hoping this would be news. In this month, they finally launched the Starliner. They didn't. And I've got to say, how many people here would be happy getting on a Boeing rocket, the way Boeing's luck is at the moment? So they had unfortunately for Boeing, and this is when your luck's out, this was the Atlas V rocket that was going to send the Starliner up. The oxygen pressure relief valve failed. I'm not sure if that increased pressure or caused less pressure in a figurative sense. Okay, so this thing, they thought it was going to go up before the before the Dragon capsule, which went up, I think, for the first time in the crewed missions on the 30th of May 2020. So it's been nearly 4 years. It's had, I can't remember, it's 8, 9, 10 manned missions. And this was the safe bet. SpaceX was the backup bet that NASA made for these things. And China's Chang'e 6 is going to land on the moon in early June. This is landing on the dark side, and it's a sample return mission. So it'll be the first time we've ever got samples back from the dark side of the moon. I know the Russians did it in the 70s, but they did it from the side facing the Earth. This one's going on the far side. So I think the race to put the next person on the moon is well and truly on, and I'm not sure who I'd bet on. Okay, so the gallery next. These are definitely the worst pictures ever shown in the gallery. They were taken by me with my lovely wife. So I said the month before last we were going out to see the solar eclipse. We saw the solar eclipse. So we got Bailey's beads on the right hand one. The middle one is totality, and the red marks you can see in the top left hand corner are prominences, and the bottom one is the diamond ring that marks the end of totality. I have to learn to focus manually on that, clearly, but I'll give it another go. And I've got to say, if ever anyone gets a chance to see a total eclipse, go. Just go. And do not be satisfied with 99 or 98% totality. Someone said to me, it is like getting a ticket for your favourite cup final, your favourite band, your favourite art gallery, and going 98% of the way there. It's not the same thing. Do totality if you can. We were very lucky, by the way. It was really cloudy, but it cleared up for quite a while, and we managed to see this. Got back to the hotel, and that's what hit us 3 hours later, which would have just ruined the whole thing. So we're incredibly lucky. Okay, so some people who can take pictures. Peter, frequent visitor here, and I'm going to say sorry about this, Peter, because you gave me a lot of notes. In fact, all of the photographers gave me a lot of good notes, and I'm doing this from memory. Okay, so this is thought to be a planetary nebula, but it has an unusual shape for a planetary nebula. As you see, they're normally much rounder, and there's no prominent central star to it, so they don't know where it came from. So it's questionable. I've put there that it took 38 hours and 30 minutes to picture this, which is quite something. I don't think it's been pictured very often. His next one, which is also Peter, you can actually see the lovely name of it, PAEL1. Okay, even longer, even slightly short, 34 hours. This is also only discovered in 2022. I don't think it's been photographed very often at all. This might be one of the few photographs anyone's ever taken of it. They're not sure if this is a planetary nebula. It does look more like a planetary nebula, or a cataclysmic binary, which is basically a white dwarf pulling matter off a larger star and then fusing periodically and throwing it out. Martin's one here. This is the Heart Nebula, which is a massive nebula which is either 700 or 7,000 light years away. It's a nursery of very hot young stars which are churning up the nebula, producing the ridges and everything you can see there. And right next to the Heart Nebula, because astronomers have a sense of humour, is the Soul Nebula. So you have the Heart and Soul nebulas, which is another one. I think this is 700 light years across. I think we're 75,000 light years away, 700 light years across. Another brilliant image from Martin, who always delivers fantastic images. I believe these two nebula, frequently they look like they're next to each other. They're in Cassiopeia. They look like they're next to each other, but they actually are next to each other. And there's a bridge of dust, I believe, between the two of them. But like I say, citation needed, because I'm doing this from memory and I've written the notes. So this one's from Stephen, the Needle Galaxy. And this was done over 3 nights. Although I think you said earlier you never do a second night. You never do more than one night.
Well, yeah,
Okay. So this is an edge-on spiral. Now, it's believed to be a barred spiral, and the Milky Way we live in, I believe, is believed to be a spiral. Absolutely beautiful one. It's about 700 billion stars. Contains about 260 globular clusters, might be 240 globular clusters, which is more than the Milky Way contains. And it has at least two satellite galaxies, and under certain wavelengths you can actually see where one of the satellite galaxies is interacting with the Needle Galaxy, which and it is in what constellations is it in?
Coma Berenices.
Coma Berenices, thank you, sorry. So that's a wonderful picture, absolutely fantastic. Okay, so any questions that I probably can't answer? Okay, all right, thank you.
Okay, if anyone spotted any errors in there, please send them on a postcard to arrive last Friday. I'm now going to hand you over to Jerry, who's going to introduce tonight's speaker. So over to you, Jerry.
Thank you, Alan. First of all, just a little update on the news. Which is that the Boeing launch that didn't, it wasn't Boeing's fault, it was with the booster. But they are currently planning to do a retry on Friday week. So look out for that, except of course it will probably be at a similar time, which in this case was 3:34 in the morning. And luckily, though, I was interviewed on BBC Three Counties Radio, and I said that I might come back to them after the flight. Perhaps I might come back to them before the flight and do another session. So on to tonight's speaker. Colin is a graduate of Cambridge and sorry, what's the other one? University. Yes, Nottingham, that's right. And he knows a lot about primary physics and mathematics. How much of that he's going to use tonight, I don't know. Something that I suspect he won't mention is that the iPad nearly could not be patented because of the effective description and showing of it in 2001: A Space Odyssey back in 1968. But there are some things that have come out of science fiction which have become reality, and some of those Chris is going to tell us about this evening. So over to you, Chris.
Perfect, no worries. So, hello everyone, good to see you. Thank you so much for inviting me along to give you a talk this evening. I love the topic of Star Wars and Star Trek. Before we get on to any of the important questions about Star Wars and Star Trek, we must of course have a quick vote on which one's the better of the two. And I think personally there's only one obvious answer, but we're a democratic society, So we're going to have a vote. A few ground rules. You can only vote with one hand. Okay. You can only vote for one of them, not both of them. Yeah, I've had some people sticking their legs up to try and vote for both of them. So, hands up for Star Wars. Okay. And hands up for Star Trek. Okay, that's probably a 70-30 to Star Trek. That's the correct answer, so thank you. Well done, everyone. So before I start talking about Star Wars and Star Trek, just a very brief introduction about who I am. I went to Nottingham University for 4 years, a long time ago, to do a master's degree in physics and theoretical astrophysics, and that got me into research. I was using the various telescopes around the world to image supernova and the polarization data from exploding stars to work out the strength of the magnetic field in the ejector of the Cassiopeia A supernova remnant. We were using something called Scuba 2, which is not quite as exciting as it sounds. It was a polarimeter on a telescope to measure the degree of polarization of these needles that were being ejected from these supernova. And it gave us some really cool images of ideas of the structure of the expanding shell of material. And we deduced that you actually have to get these strong kind of long needle-like materials which can generate such a strong magnetic field, really much higher than we'd previously thought. And that got me interested in research, and then I applied to Cambridge and went to do part 3 mathematics, just to kind of prepare myself for a real job involving maths. And then I got to Cambridge and I was lucky to work down the corridor from the late Professor Stephen Hawking, and I was inspired by him as a kid, and I was reading his books, A Brief History of Time, and my favourite one was The Universe in a Nutshell, because it was highly animated with lots of pretty pictures, which as a teenage boy was easy to understand. So I was lucky to stay in Cambridge, and I did my PhD there. I worked for the European Space Agency as part of the Planck satellite research team. We looked at the very early universe and tried to model the cosmic inflation in the first femtosecond after the Big Bang, and look at the radiation signatures that this would produce in the cosmic background radiation. And we tried to build models of different types of inflating universes and what kind of signals these would generate in the data that we could see. Day to day I was just coding in LaTeX and then coding in C for about 12 hours a day for 8 months. That's the real job of an astrophysicist, is programming 8 hours a day. My final code had about 40,000 lines in, and it took about a week to run on the Cosmos supercomputer, which was at the time one of the fastest academic supercomputers in the UK. And I kept getting faults for about 3 months, and the output of my code was a single number. This huge script was running, and it would output a single number, which was the probability of the universe being the model that we proposed. And after about 3 months of it not working, finally I worked out how to fix the code and waited a week, and this single number came out, and I remember jumping in the air for joy at a single number. That's the life of an astrophysicist. So I then, at the end of it, I decided to create a small company, and we build observatories around the world for people that want to build them in their houses, and we try and build not quite research grade, but kind of public observatories that some people would like to share with their local communities. And we set up a group called Astronome Limited to do this, to focus on kind of bringing together all the pieces to build observatories for people that can afford them and would like them. I now work at Harrow School in London, and I'm lucky to be the head of astronomy there, and we have a large observatory called the Raleigh Observatory, just on the outskirts of London. It's on the roof of the physics department, and we use the observatory to do kind of interesting research projects with the kids. We try and get them into university, and many of them want to go and study physics and astrophysics at university, so we try and get them published before they go to university, and that's a real tick box for these universities. If they see that students have done some research, they're more likely to give them a place, particularly some of the higher level Russell Group universities. We work on fun projects like imaging or timing the rotation of near-Earth objects to estimate sizes of there's many thousands of these objects you can image, and not many of them have been imaged very well. You can look for this periodic variation in their brightness, and you can work out the size and shape of these objects and add to the public catalogue. And we do some astrophotography, and we try and do some stellar spectroscopy as well. We built a simple spectrometer, the boys at the school built it, and we try and get down to about a 5 nanometer resolution, for those who know about spectroscopes. Basically, we look at the rainbow of light from these stars and try and work out what category of stars we can see in different parts of the universe, mostly our galaxy. And we created a company called Caribbean Sky as part of the work with the Astronom company. And one of the observatories we built was in the Caribbean, and we wanted to share it with all the public in the Caribbean. It was in some rich guy's mansion, but we wanted to try and share it with all the school kids. So we set up a company called Caribbean Sky, which was a private website, and we share it with all the schools in St. Lucia, St. Vincent and Martinique and all of the islands in that part of the Caribbean. And we give the teachers pictures and videos and resources that they can use with the kids in their class. The goal was to give the kids a picture that was kind of taken on their doorstep rather than taken by the Hubble Space Telescope. And that has been really fun as well. On a more boring note, I'm the chair of exams for GCSE astronomy. Not quite as exciting as the other ones, but I help to write the papers and examine them and consider any syllabus changes that we might want to do for the next time that we change the course every 5 or 10 years or something. So all of the topics I'm going to cover today can be researched and referenced to these glorious Haynes manuals. There's one of these for the Starship. Is that the Enterprise? I'm not sure. The first one, the Enterprise, and of course the Millennium Falcon. So all of the technical details can be uncovered in these Haynes manuals, available from any good booksellers. So the topics I'll try and go over tonight. First of all, how far away is space? How big is it compared to what we know from the Star Wars and the Star Trek eras? How far have we got to go and capture the nearest Borg craft? How far are other galaxies? How big is it compared to how Star Wars portrays it? Well, suppose we don't want to fly there ourselves. We want to teleport ourselves. Is that possible? What kind of cool techniques can we use to teleport matter across the universe? And has that already been achieved in parts of the world? Of course, when we get to the other side of the universe, we're going to need some weaponry to defend ourselves. You might not have a lightsaber or a phaser or a photon torpedo, but what stage can we get to? Can we build lightsabers? Can we destroy planets with Death Stars? An interesting question that many students want the answer to. Now, many of my students study physics, and I'll say, well, why have you studied physics? Well, I quite enjoy blowing up stuff, and I want to know if you can destroy a planet. Of course. There we go. That's better. Can you hear me again? Good. So let's start off with how far away space is and how far we've got to go to get to our neighbouring stars. One of our closest stars, in fact, our closest is called Proxima Centauri. I think it's in a binary system with Alpha Centauri here. You can't really see it from the northern hemisphere, but for those who've been to the southern hemisphere, you can spot it quite easily by finding the Southern Cross, quite an easy constellation to recognise, and following the short arm across to the bright star Alpha Centauri, which you can just about see with the naked eye. Proxima Centauri is a little bit too dim. I think it's maybe magnitude 7 or 8, so a little bit too dim to be seen with the naked eye. But this is our closest star. Now, our closest star is about 5 light years away. This will take a long time to get to. Several tens of thousands of human generations, perhaps. The most distant craft that we've launched as humans are our Voyager probes, and these use the gravitational slingshot of the outer planets to speed up the craft as they left the solar system. I think Voyager 1 and 2 were launched in 77 or 75, something like that. This animation on the left shows you this cool gravitational slingshot that you can use the outer gas giants to speed up your escape from the solar system. But this still takes a long time. Even at the high speed that you can get to using these gravitational slingshots of 60,000 kilometers per hour, it would take 76,000 years to get to even our closest star. So that's not possible. So we need some other kind of tech. We can't just keep burning oxygen and in our rocket ships. We need some other kind of more powerful technology. And there are 2 likely candidates that we could, in theory, build. The first one of these has already been used successfully on several probes so far. It's called an ion engine. And an ion engine uses ionized material to accelerate craft at a very low rate. You can just make tiny adjustments to the velocity of your spacecraft. These ion engines will get from 0 to 60 in about 4 days' time. So you probably won't see Jeremy Clarkson reviewing these anytime soon on Top Gear or whichever program he's not been fired from yet. So even with the ion engines, 10,000 years it would take to get to our closest star, and it would take a long time to accelerate up to that speed. Still several hundred human generations. These have been used successfully on many probes. Here is the view inside one of these ion engines. This cavity in the center is where the ionized material is stored, and this is then ejected using strong electric and magnetic fields to push this kind of vapor out the back of the engine. And the good thing about it is they're quite flexible. You can turn the engine on and off quite easily. You can't really turn a rocket off very easily once you've started firing it. It's more difficult to do. So the fuel lasts a long time. The fuel can, in theory, last 10 or 20 or 50 years with your craft. The basic idea is that you ionize the material by heating it with a strong voltage. Then you fire it through these grills, and these grills capture some of the lighter elementary charges, the electrons, I think, and the heavier particles accelerate out the back, and this produces a tiny thrust that pushes this engine a little bit faster each time. These have been used on 2 of the NASA probes, Deep Space One and Dawn, and these were investigating asteroids in the solar system. Dawn was the first spacecraft to orbit 2 different extraterrestrial bodies, the first spacecraft to visit either Vesta or Ceres in our solar system, and the first to enter first one ever to orbit a dwarf planet. The first NASA mission to use this propulsion and enter and leave the orbit of 2 of these asteroids was amazing to see, and these ion probes are quite exciting for investigating objects in our solar system. The idea of this tiny acceleration is helpful because you only need to make a small adjustment to your orbit. The next time you go around, you might end up at an asteroid which is tens or hundreds of millions of kilometers away, just with a tiny change in velocity. You don't need very powerful rockets to adjust your trajectory by a small amount in the solar system. The second possibility is a much more exciting type of engine, one that my students particularly enjoyed learning about. It's called nuclear pulse propulsion. This was first proposed a long time ago. I think the first ever paper was just after the development of the nuclear weapons in the 1940s and the 50s. The USA did a research a project about this in about 1960 and looking to see whether they could build one of these in the 1960s and the 1970s. The idea is beautifully simple. You take a rocket ship, you load a few hundred nuclear weapons onto the rocket ship, you blast into orbit, you throw off one of the nukes behind you, you detonate it, you ride the shockwave, you throw off a second nuke, blow it up, ride the shockwave, and then after like a few hundred nukes, you get pretty close to, a decent fraction of the speed of light. Now, there's a few minor health and safety issues that may go along with this, but the proposals found that for every rocket they launched, maybe just a few people would die on Earth as a result of the radiation poisoning, and some would say, wow, a few people, that should be okay. But unfortunately, health and safety, again, won the battle, and they didn't ever look into using these. But with the speeds that these rockets could get to, we could in theory get to Proxima Centauri in about 100 years, which is only a few human generations. You would only have to explain to your great-grandson why you left Earth in the first place when you got there. So, and again, a nice possibility. And this is within the realm of our current tech. Pretty cool. So the closest planet may take about 100 years to get to, even using a nuclear pulse engine. But what about even further objects in our galaxy and further afield? Well, the closest potentially habitable planet we think may be 170 years away using one of these nuclear pulse engines. One of the closest planets that has signatures of water in the atmosphere. We think it has a magnetic field. We think it has all the conditions that could be suitable for sustaining life itself. Further away, the closest exploding star, suppose that we want to go and capture some rich Earth resources, some exotic metals from the nearest supernova. This would take about 15,000 years to get to with one of our nuclear pulse engines. The center of the galaxy, suppose we find some cool black holes or some cool signals of life coming from near the center of our Milky Way. This would take a few million years to get to with a nuclear pulse engine. The Large Magellanic Cloud, visible from the southern hemisphere, a beautiful cloud of stars that you can see in the night sky, would take even longer to get to, almost 4 million years. The Andromeda Galaxy, our closest neighborhood giant galaxy, would take 50 million years to get to. But Andromeda is actually coming towards us, so if you just wait about 5 billion years' time, then you haven't got to go there in the first place. Andromeda is going to collide with the Milky Way in something like 5 billion years' time. And even more distant galaxies, hundreds and hundreds of millions of years with our nuclear pulse engine. So we're limited ultimately by the fundamental constants of nature. Einstein's speed limit. Here's Einstein with a speed gun saying you can't exceed close to 300 million kilometers per second. This is the cosmic speed limit, the speed of light. We've found no way yet of breaking the speed of light. There was a research study which came out about 5 years ago claiming that they'd found a way of sending signals faster than the speed of light. It turned out to be a technical hitch. They had forgotten that they'd added an extra wire in their circuit, so they thought it had travelled further than it actually had. So unfortunately, they didn't break the speed of light, and we don't yet know of any way of doing this. Einstein proposed this theory over 100 years ago, this cosmic speed limit, when he first looked at his ideas of kind of relativity and the giant scale of the universe and objects radiating light and how long it would take that light to get around. And we've still found no way of breaking Einstein's cosmic laws yet. So is he going to be correct? Is he going to limit us? Now, of course, in both of the series, Star Wars and Star Trek, we can go faster than the speed of light. It would be a very boring film if it took hundreds of millions of years to get to M51 or any other neighbouring galaxy. You might remember the phrase when Han Solo shouts, "Punch it," in the Millennium Falcon, and you get this beautiful cosmic effect where the stars start to shine in these beautiful lines, and you know this is when they're going to warp speed, faster than the speed of light. Unfortunately, the stars wouldn't really look like these cool lines, unfortunately, but it's a good cinema effect. Again, when you're producing a Hollywood film, you've got to exaggerate the laws of physics a bit to sell some tickets. But this is when the Millennium Falcon accelerates into hyperspace. As Scotty would say, we need more power, Captain. And a warp drive is the way that the Star Trek universe get us to go faster than the speed of light. These warp drives do exist in theory. They're called Alcubierre drives, and these were proposed many, many years ago as a way of potentially moving or getting objects to appear to move faster than the speed of light. The problem is you can't move things through space, so you just squash and stretch space instead. So this animation on the right shows you the idea behind this Alcubierre drive. We're not really moving the spaceship at all. We are just compressing the space-time in front of it and expanding the space-time behind it. We do this with exotic kinds of matter. In the same way that we sometimes talk about matter bending space, like causing objects to orbit around and produce gravitational fields, with negative mass, it's a hypothetical type of mass, space can bend the other way. So we get some negative mass behind the spaceship, we get some normal mass in front of the spaceship, and this can push or move our spaceship apparently faster than the speed of light. Again, there's a few, one or two issues with this. This stuff called negative mass, we haven't yet found it. It doesn't exist, and it doesn't exist in any of the laws of physics. And the energy that we need to move a craft is more than the energy contained in the entire universe. Again, just a small problem with this Alcubierre drive. But it's a nice idea that science fiction still thinks there could be a way to produce it if we find this exotic negative mass in the Large Particle Collider in CERN or in outer space in other places. If you turn to page 34 of your Haynes manual, you'll see this lovely diagram. And this tells us how fast the spaceships are travelling for whichever warp factor the captain decrees. Picard may say warp factor 9. And warp factor 9 is a number representing how many times faster than the speed of light you're travelling. So you're travelling at warp factor 1, you're going about the same speed as light and same speed as the speed of light. And for each additional warp factor you add on, you increase your speed. Bear in mind the scale on this graph is logarithmic, so every step up you go, you increase by another factor of 10. And warp factor 9 was the traditional maximum speed of the starships in the Star Trek era. You had to have exotic creatures that could allow you to communicate or send signals faster than the speed of light. Let's suppose that we went at the traditional maximum speed of the Enterprise, warp factor 9. Well, even at this incredibly high speed, it would take 24 hours even to get to the closest star at warp factor 9. Again, something that the series don't quite let on about in the episodes, that even at warp factor 9, it takes a long time to get around the galaxy. Okay, the other side of the galaxy would take 100 years to get to at the maximum speed of the Starship Enterprise. There was one of the series of Star Wars, Voyager, I believe, with Captain Janeway, where part of the plot was they got thrown into a Bajoran wormhole, teleported across the galaxy to the other side, and then spent the next 8 or 9 series trying to get back to Earth. This was the image of the Star Trek galaxy as they knew it then. The entire region of explored Federation space was this small section here. This is it. Where did Voyager get catapulted to? Across the other side of the Milky Way, into this Bajoran or Borg space on the opposite side of the galaxy. It's a big place, even at warp factor 9. So even the Starship Enterprise at maximum speed may not be able to get us that far. Here's a nice video showing our rough size of the Milky Way. And I always like to share these videos as a visual way of seeing quite how big our galaxy is compared to our tiny patch of space. So travelling across the galaxy takes a long time. We've got to first get out of the solar system. Having zoomed in to look at our local neighbourhood region of the galaxy, we've got to zoom in by another factor of 10,000, even to see the very outer region of the material which gets impacted by our sun. Another factor of 1,000 in, and we can start to see the inner planets. So our Milky Way is a huge, huge place. It takes a long time to get around. You may remember this clip from one of the original Star Wars films when the heroes left. So if we can't use these warp drives and it takes a long time to get around, what kind of problems might we encounter as we're travelling around our solar system or trying to return back to our side of the Milky Way? See if you can remember this scene from one of the original series.
You're not actually going into an asteroid field.
They'd be crazy to follow us, wouldn't they?
You don't have to do this to impress me.
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds. Be around. I made a mistake. This could be it, sweetheart.
I take it back.
So an exciting scene to watch. And so it gave lots of young kids the impression that space is full of these asteroids, and that were we really to fly through the Milky Way, we'd spend all of our time dodging the asteroids and swerving out of the way. Unfortunately, it's not quite as exciting as that. Asteroids are really such a huge distance apart that the chance of even seeing one this closely, you have to be going straight towards it. The only place you might get close to that in our solar system is probably the rings of Saturn. Even the asteroid belt between Mars and Jupiter, there are many millions or tens of millions of asteroids there that are pretty large, but the chance of any two of them being close enough that you might have to swerve to avoid them is close to zero, unfortunately. The rings of Saturn, again, may be the closest you could get to this asteroid-infested part of the solar system if you were flying across the centre. But the majority of the rocks in the rings of Saturn, they're not big asteroids. They're just small kind of bits of dust and pebbles and very, very small rocks. So not quite as exciting as the video, unfortunately. This is an artist's impression of what you might see if you were flying across the rings of Saturn. And this video makes them look a bit bigger than they really would be. Most of these things we think are just kind of small rocks. There's no huge asteroids like we could see in the previous video. So let's suppose hypothetically that the solar system was full of these giant asteroids and we really did have to swerve to avoid them in our spaceship. Well, instead of sending a spaceship, we could perhaps teleport people as well. Teleportation was as a great visual effect. When you want to send your crew down to the planet, it was often cheaper to film them teleporting than filming a ship landing on the planet. And so teleportation is featured in both Star Wars and Star Trek, and even Stargate. Any Stargate fans? A few nods. Even further back. And many other space shows have also featured teleportation as a concept as well. The idea of teleportation is relatively simple. You obliterate your creature, you turn them into a beam of light, you send them to the teleportation chamber. You've got your signal now. You send the signal to the other teleportation chamber, wherever that may be, or even down to the surface of the planet. And then you rematerialize your your Ewok or whoever at the other end, and you hope that the signal has all got through correctly. That's the kind of idea. It's nice and simple when you explain it that way. You're converting matter to energy, sending a beam of radiation down to the planet or wherever you want to teleport them to, and then somehow rematerialize them at the end. Now this seems incredibly far-fetched, but it's already been achieved on a very atomic scale. So teleportation of individual particles has already been achieved. This is a view from one of the telescopes in the Canary Islands. I think this might be the one in La Palma, looking across to the other observatory up in maybe it's Tenerife, maybe it's La Gomera. And this is a image showing you the path that was taken by one of the successful teleportations of a single atom. It was one electron was teleported something like 60 or 70 or 100 kilometers across the gap between these islands. This was first achieved in 1998 in an experimental laboratory in the USA. They then achieved the same thing a few years later, 600 meters across between two laboratories in the same university. And then a few years after that, in 2012, they did it 150 kilometers between La Palma and Tenerife. So they successfully teleported one electron, one fundamental particle, 150 kilometers. Now we've got a long way to go before we can teleport an entire person. The idea behind this teleportation is a cool application of quantum physics. Now, quantum physics is quite an interesting topic. I think it's interesting, but I'm a massive science geek. Many of my students don't find it quite as interesting as I do. So I show them this picture to try and explain a concept called quantum entanglement. And this is the idea that if you have two particles like electrons or protons, you can mix them together and then send them as one signal, and then at the other end, if you change that signal at all, then one of the electrons should pop out at the other end. And so this picture is a nice way to visualize it. If you imagine moving one of the kittens, the other one will have to move as well. This idea of entanglement between particles is when you change one, the other one must also automatically change, even if those particles have been separated by a large distance. So quantum entanglement could, in theory, teleport Spock from one side to the other, but you'd have to be sure that the signal wasn't degraded, or the weather didn't get in the way, or your transmitter didn't run out of power halfway through, because Spock might end up at the other end with a few more problems than he left with. And would you really want to step into a teleportation chamber? It's an identical version of you at the other end, with all the memories, thoughts, feelings, happiness, sadness. And the person who steps out feels like they've just stepped in, but it's not really you. You've been obliterated at one end and recreated exactly at the other end. It's an identical clone of you, but it's not really you. I'm not sure I'd be too happy doing that. There's a few issues with it. One of them is we need to store all the information. So storing all the information for every atom in a human body takes something like 100,000 trillion gigabytes of storage to store all the information about every atom in your body. There's 10 to the 26 or 27 atoms in your body. That takes a lot of memory to store it. You're going to need to upgrade your computers if you want to store that. Millions of computers will be needed. Then you've got to convert the entire human body into energy. And using E equals mc squared, that means it's quite a lot of energy. Right? If the average person weighs something like 60 kilograms, if you put 60 kilograms into this, that's quite a lot. The tiny balls used in some of the nuclear weapons that were developed in the World War II era were just a few kilograms in size. So a human being much bigger than that and might release the same energy as thousands of nuclear bombs. Again, just a minor health and safety concern that we'd have to deal with if we ever decide to do this. Interference would almost certainly get in the way. Could you transmit that huge signal from one planet to another without losing any of the signal? I'm not sure. Particularly not with the British weather. Imagine you wanted to teleport from University of Hertfordshire up to Glasgow for the day. Would you trust the British weather to keep your signal perfect on that 300 kilometres? I'm not sure I would. Again, you might find that one half of you gets lost in transmission, unfortunately. And then the hard bit of it is to rematerialize this light beam into matter at the other end. Now, E equals mc squared is good, and it's quite easy to convert mass to energy, but it's even harder to convert energy back to mass again. That takes a lot more energy than it takes to blow something up. So rematerializing one human body at the other end would take, we think, several thousand suns worth of energy. Again, it's not saying it's not possible, it's just not likely. And then we've got the philosophical issue that it's not really you. And again, I wouldn't be very happy standing in a teleportation chamber, because I know that I'd be vaporized one end and an exact clone of me would appear at the other end. I'm not sure I'd be too happy about that. So suppose we don't ever get to build one of these teleportation chambers, but we still want to travel across to the other side of the galaxy. So we just look for a wormhole, right? These are always featured in the Star Wars and the Star Trek series as gateways to the other side of the universe. And if we can't travel above the speed of light and we can't teleport people, then maybe we can just use a wormhole. A wormhole is a theoretical tunnel through space. So you jump into one side and you pop out somewhere else in the universe. Might be in the same galaxy, might be on the opposite side of our known universe. These wormholes were actually first proposed by Einstein in some of his early sketches. He didn't propose them as tunnels that could teleport you. He just proposed them as areas that you might enter after you've fallen into what he called a dead star, which we now know as black holes. The idea behind these wormholes is that we can bend space. I mentioned earlier about the bending of space-time by when we were building our warp drives. And this image shows you this bending of space. We have the Earth in the center, which bends all the space around it, and that's what causes the planets the Moon in this case, to orbit around the planet. We always think of planets as orbiting in circular or elliptical paths, but really they're just traveling in straight paths on bent space. If you were on that moon and looking forward, you would see yourself following a straight line. And that's one of Einstein's great ideas, was that things aren't really moving in elliptical paths, they're traveling in straight lines on bent space. So this idea of bending space is crucial to the idea of wormholes. And the idea is that you keep on bending space with bigger and bigger objects, more and more mass. You start with a small star, it doesn't do much. You double the size of your star, it starts to bend space and bend light a bit more. Larger and larger stars create bigger and bigger bends in space-time. And the theory proposes that if we have a large enough star, maybe we can even break open space and cause a tunnel or something that we might enter into if we were to jump inside a black hole. This is the sketch of the wormhole as seen in the Haynes manual of how to use your local wormhole to teleport around space. And so traditionally, you follow the red line. You have to go all the way around here to get to the other planet. But if you find a wormhole, you can just jump in here. It's a black hole. You build a spaceship that can withstand falling into a black hole, and you just pop out the other end in what we know as a white hole, the other end of the tunnel. That's the idea behind the wormhole. Unfortunately, this violates a huge number of laws of physics and nature, so we think it's unlikely that this will ever be able to be seen. And as well, if you were to find the local black hole and you were to send a spaceship into it, the people who entered it wouldn't be able to communicate back to you. Once they've entered the black hole, they can't radio back and say, "Hey guys, it's actually pretty warm over here," because the light from their radio can't escape the black hole. We would never hear from them again. Other unfortunate effects would also happen as you fall into a black hole, but that's a topic for another day. One called spaghettification, which is where you get stretched out into these super thin lines like spaghetti. That's one thing that astronomers have named well, I think, spaghettification. So, we don't have wormholes, we don't have faster than light travel, and we don't yet have teleportation of an entire spaceship. But wherever we go, if we find aliens who perhaps aren't as friendly and as welcoming as the humans are, perhaps we need some weapons to defend ourselves. This is a lovely comic illustrating how all these strange aliens have another bizarre character with a fantastic weapon. All of the weapons that were used in all of the series of Star Trek and Star Wars were all based on light. You might remember the terms phasers, photon torpedoes, disruptors, and lightsabers. All of the weapons were based on light. Indeed, the most powerful weapon using light was the Death Star, was Vader's creation. The Death Star was the giant kind of spherical shaped spacecraft that had the most powerful laser that had ever been produced. You may remember this phrase from one of the original series. This video. So there was a Class M planet being destroyed by the friendly named Death Star. Now the Death Star could destroy planets, and that was the idea. Darth Vader could move the Death Star around, and without having to worry about killing the people, he could just destroy the planet. That was much easier than genocide on the planet itself. Again, of course, this is a topic which my students quite enjoyed doing. They don't do many homeworks when I ask them to, but when I said, can you calculate the energy we need to destroy a planet using the Death Star, all of a sudden they handed in their homework early. So maybe that tells us a tale about the teenagers of today. I'm not sure whether I should be worried or not. But to destroy a planet, we need 220,000 billion joules of energy. That's a big number. That's about 1 week of the sun's total energy. If we could somehow capture all of the energy produced by the sun in about 1 week, focus that into a laser and shoot a planet, we could, in theory, destroy it. Okay. And for those of you who are keen mathematicians, there's the actual equation that you can use to work out the energy required the energy required to convert all the gravitational potential energy into a cloud of gas and dust expanding into space. So we're nowhere near building a Death Star, thank God. But one of the most powerful lasers ever produced is this one. This is called the National Ignition Facility. This is in the USA, and this is a research center trying to create sustained nuclear fusion. So you might hear that nuclear fusion is still only about 20 years away. When I was a little kid, it was about 20 years away. I think it's still 20 years away, and hopefully in 20 years it may be less than 20 years away, but I'm not quite convinced. Although there is some quite regular updates that they've almost achieved sustainable fusion. I'm not sure what the most recent story on that is, but hopefully we can use these nuclear fusion reactors to solve humanity's energy crisis. Now, this is the most powerful laser ever produced. And compared to weapons like the nuclear bombs that were dropped on Japan in the Second World War, this laser produces a lot of power for a very short amount of time. It's not a sustained laser pulse. To give you an idea of quite how powerful some of these explosions are, the biggest weapons that humanity have ever produced. This is a graph showing you the relative size of the bombs that were dropped on Hiroshima, the Trinity test site, and then some of the larger bombs that the US produced, Mike, Bravo, and then the Tsar bomber that was made by the Russians in about the 60s, I think. These weapons are kind of terrifying to see, of course, and kind of scary that we've used science about nuclear fusion to build weapons. These Tsar bombs, this was the most powerful detonation ever produced by mankind, and we need about 1 million of these bombs given to every single person on planet Earth to destroy the Earth, which is reassuring, I suppose, because I don't think even the Russians have 1 million billion of these bombs to hand, ready to give out to all the people. But if we gave every single person on Earth 1 million of these bombs, that would just about destroy the Earth, we think. This is the remaining the crater left by the Tsar bomber. You can, in fact, go and visit it. There's a little visitor centre down here, although I'm not sure you can at the moment. But that's the kind of the wreckage that we leave from these huge bombs. So reassuring that even with the most powerful nuclear weapons at the moment, we're nowhere near destroying a planet. We're not going to give everyone on Earth all of these bombs. To get all of the energy from 10 of our suns together to try and build a weapon to destroy the planet is an unlikely thing to do. So at least we're nowhere near destroying our planet using a Death Star yet. We may, of course, destroy it other ways, but we're not going to be destroying it with a Death Star anytime soon, thank God. So perhaps instead of building Death Stars, you might want to think about the weapons used in the Star Wars and the Star Trek era. And there's a great phrase at the start of one of the original books of Star Trek that says, Star Wars, that says, "In a galaxy far, far away, with Jedis who keep the peace, the Siths who plot to overthrow them, teddy bear insurgents called Ewoks, and a princess who flies through space, the lightsaber is the most iconic weapon to wield." And as Obi-Wan Kenobi said to Anakin Skywalker in Attack of the Clones, this weapon is your life. Can we build these lightsabers? Yeah, the answer is kind of, yeah. Last year, a Canadian engineer and the CEO of Hacksmiths Industries, James Hobson, created this cool plasma proto-saber, something out of the Star Wars universe. The proto-saber was originally a predecessor to the lightsaber. The proto saber had a huge battery pack that you had to wear in a rucksack, and that would provide the power for generating the plasma beam. So this was the precursor to the more famous lightsabers. Here's a video showing the power of this really cool invention.
Prepare to meet your destiny.
Oh, hey there.
I think that poor kid's terrified.
Stepping on my tape. That's scary. This thing is so cool, oh my god. Prepare to meet your destiny. Obi-Wan, your tape looks flammable. Are you ready to?
So there we go. We can build proto sabers, just as in the Star Wars universe. These were the precursors to the more modern lightsabers. This guy's got a big gas tank on his back, which is providing all of the fuel to produce the plasma. There's a few minor health and safety issues that we might have to deal with there, but pretty cool that they can make it glow bright red by putting some salt into the plasma tube. You can change the color of your lightsaber to any color you want. A slightly less exciting one, but still technically a lightsaber, is shown here. This is a stream of gas, so instead of a stream of plasma, this is a kind of a relatively low energy stream of plasma, which is being bent by the strong magnets in the base here. This is perhaps a slightly more elegant weapon for a more civilized age, but this one, as you can see, doesn't quite have enough energy even to cut through a paper stormtrooper. So I think, again, we're still a long way away from killing people with these. So lasers, we know, are important, and I've spoken about how light can be used to build all of our weapon systems. And we need some lightsabers or lasers of some kind. Perhaps our weapons must always be light-based. And there's the next few stories I'd like to tell you about a story mentioned in this book called What If? This is a great book that I love to recommend. It's by a guy called Randall Munroe. He's an American guy who wrote the online series What If? And XKCD, some really good kind of web comics about kind of geeky science stuff. And this book asks quite absurd scientific questions, but then tries to answer them with scientific reasoning and scientific rationale. And one of the questions that he asked in this book is quite reasonable. If every person on Earth aimed a laser pointer at the moon at the same time, a bit like the laser pointer I have here, the small red one, would it glow? It's an interesting question. Right? This is a pretty low-powered laser. The moon's a long way away. So he goes through a series of proposals to try and test these scientific ideas. And this book is full of these kinds of cool sci-fi type questions. Well, with a few billion of these tiny laser pointers, we have absolutely no effect at all on the surface of the moon. Again, perhaps unexpected, but we're scientists, so we should keep going and see how powerful we've got to get to before we can start illuminating the moon with our lasers. Well, I've got a slightly more powerful laser. This is a laser that I use for stargazing parties. This is almost certainly legal to buy in the UK. I bought it in a Hong Kong night market. I was giving some astronomy lectures on a cruise ship many years ago, and I realised I'd left my laser at home for the stargazing parties that I was asked to host on the ship. And I went to the Hong Kong night market, and one of the locals came up to me and said, "Oh, I've got anything you want, sir. T-shirts, flasks, whatever you want, tourist stuff." And I said, "Okay, I need a bright green astronomy 1-watt laser." And he went, "Yeah, you are, sir. It's $10. So here it is. This is a $10 purchase from the Hong Kong night market, an astronomy laser pen. This thing is incredibly powerful. It looks a bit like a lightsaber when you shine it up late at night. So if you like one yourself, you can buy them more legally on wickedlasers.com, and they're just about dangerous enough that they hurt your skin. And if you shine it on your skin, you can feel it burning after about 5 seconds, which tells you that it really is dangerous and that you shouldn't really use them for anything. So if we upgrade everyone's lasers to a really powerful laser, sadly, there's still no effect on the surface of the moon. So we've got to go up in power again. We're all scientists, so we need to investigate what happens at the end of the situation. So, the most powerful laser beam, powerful projector beams on Earth are the IMAX projectors array. Some of you might have been to an IMAX theatre before. There's a couple in London. These have really, really powerful projectors. And some of these projectors can use up to 30,000 watts of power. It's over 1 million candles worth. Surely with 6 billion of the IMAX projectors, we might start to make a difference to the brightness of the moon. Sadly, no. We need to go up further. What have we got else? Well, the most powerful spotlight in the USA is on the top of the Luxor Hotel, the pyramid-shaped hotel you might have seen in the photographs. If we pointed every one of these up at the moon, would we make any difference? This is another 10 times more powerful. This shows us quite how much power we need to even illuminate a moon, let alone blow it up. Let's push the boat out. In the 1970s, the US and the UK military investigated mounting lasers on Boeing planes to shoot down incoming intercontinental ballistic missiles. These really powerful lasers could basically heat up these incoming rockets and cause them to fall out of the sky. So in a 747, we could mount one of these Boeing YAL-1 lasers, and these were at the time the most powerful lasers ever produced. This would be a megawatt worth of lasers, and finally we're starting to have an effect. We'd only need the most powerful ever military laser mounted on every square metre of Asia to finally make a difference in the brightness of the moon. This would then give us a bright moon which would be even brighter than the sun. Now we'd burn up the Earth's oil reserves in about 2 minutes, so that again there'd be a few health and safety issues that we need to deal with for that case, but we'd finally have some scientific success. But we don't stop there. We go even further. We use the current most powerful laser beam ever produced by man. That's the National Ignition Facility laser that you can see here. And we pretend that we use it continuously. When this laser fires, it only fires for a tiny, tiny fraction of a second to pulse the material in the center of the reactor. So we somehow redesign it to continuously power and continuously fire. Again, we don't yet know how to do that, but we'll give every single person on Earth one of these National Ignition Facility lasers. Well, the entire Earth's atmosphere would be instantly ignited. The entire Earth's atmosphere would be aflame, and that would kill us all. The reflected light from the moon alone would boil the oceans in about 3 days, which would again enhance the thickness of the atmosphere and make the atmosphere even hotter. That would then also ignite due to the power dumped in the air. But more interestingly, it would produce an interesting effect on the moon. So much energy would be dumped onto the surface of the moon that it would kind of vaporize the upper layer of the moon's surface. These tiny particles that had been vaporized would act like a very, very small thruster, slowly pushing the moon away from the Earth. So, after about a week or so, maybe 2 weeks, the moon would in fact leave the Earth's orbit due to its extra thrust and enter its own somewhat chaotic orbit around the sun, and may indeed eventually come back to hit the Earth on its next time around the sun. So we'd have no moon left, and we may not even have an Earth left, and we may decide at that point we've perhaps used too much power. But it's an interesting thought experiment, and if you'd like to learn more of these kind of silly but entertaining experiments, I do recommend the Randall Munroe What If book. So the last thing to discuss is life forms. And this, again, is a question which people often have their own opinion on. Now, all the aliens in the Star Trek and the Star Wars era were surprisingly humanoid in form. I think it was often cheaper to get actors that were somewhat human than hiring your local aliens. Now, there are two ideas behind civilizations and two ideas behind where they come from. But how many worlds could there be out there that could support life? Our galaxy has something like 100 billion stars or a few 100 billion stars, and most galaxies are the same. We now know that our observable universe probably has up to 1,000 billion galaxies, or perhaps even more, now that the James Webb Telescope has discovered galaxies that formed so early on. So all of these 1,000 billion galaxies, on average, will end up with a few 100 billion stars. We now know that most stars have at least one planet. Some have an entire planetary systems. Some don't have any, but there are, on average, there's probably one per planet, one planet per star. And then we come to the idea of this. You've got to take this with opinion, because the numbers that I put in here are just random choices. Let's suppose that 1 in 100 planets were habitable. And that's something like what we found so far. Out of the 5,500 planets, there are maybe 100 or 200 that could be habitable. So that's a reasonable number. But you can play with these numbers a bit. Well, let's suppose we have the conditions for life. We have water, we have an atmosphere, we have a magnetic field. Maybe only 1 in a million of those would ever go on to evolve life. And of those that evolve life, only 1 in 100 of those life forms become intelligent. That would still be 100,000 million habitable planets with intelligent life forms on. And that would raise even the eyebrow of Jean-Luc Picard, I think. But that doesn't mean that we'll ever communicate with life. And again, it's another interesting topic for discussion is what's the chances of us ever communicating with life? They might be billions of them out there, but will we ever talk to them? Well, this guy wondered that same question. This is, I think, Professor Frank Drake, and he produced something called the Drake equation in the background here. This is still on the astronomy GCSE. This is not one of my students tattooing it on their forearm. I wondered how you would reprimand them for that, and whether you could count it as cheating. It's pretty dedicated cheating to get the equation tattooed on your arm. I mean, students often sneak in a bit of paper, but put it on your arm. I mean, give them credit where credit's due. I would give them an extra mark for tattooing the Drake equation on their arm. And each of these numbers factor in concepts about how long does a civilization exist for, how long can it broadcast its signal into life, how many new planets are being created, and how long does a civilization last for. Civilizations may be destined to only a few hundred years after they've got to a certain level of intelligence. Look how close we've come in the last 100 years. And when you put estimates into this equation, you get a much, much lower number. The number of civilizations that we could communicate with in the time that humans exist is somewhere between 1 and 100 million. Again, nowhere near the huge number that we had before, but still greater than 0. Maybe that's the reason why we should keep searching. Amazing thing to discover. And what would the life look like? Well, the two ideas for life forms being out there are panspermia and independence. Panspermia is the idea that life can spread around the universe by asteroids smashing into planets. This can release material out of the planet itself, small rocks and pebbles, and those rocks may have basic bacteria that can survive in outer space. That they can then drift off into other solar systems eventually, and they can land on other planets and then kickstart the evolution of life once more. So with those panspermia life forms, they might also be humanoid in form because they've all started from the same bacteria. This is a nice cartoon showing you this is a bacteria riding a rock into another planet. This is how life could have been started on Earth. It's a pretty unpopular scientific theory, but it's a theory nonetheless. The idea that life can spread around the universe in these bacteria. So you only need one planet to evolve life before it can populate the rest of the universe. Independence is perhaps a more favourable idea that any planet, regarding the conditions that it has, it could be hot, it could be cold, it could be snowy, it could be icy, it could be covered in radiation. Whatever situation you give life, life can evolve. And many astrophysicists believe that life is pretty likely out there. Again, it's a topic of conversation. It's quite an opinionated topic. And I personally think this is quite likely. I believe that life's almost certainly out there somewhere. I don't think we'll ever communicate with it in the time that we're here on Earth, but I'm sure they're out there somewhere. And this is a nice video I'd like to show you towards the end. The video I'm about to play you shows all of the discoveries of planets since the first ever planets were detected. In 2024, we're up to over 5,500 detected planets. You can see these predictions as notes which appear in the video. Every ping that you hear tells you the location of the planet. The pitch of the note is where in the galaxy the planet is. The low pitches are close to the center. The color is the discovery method that was used to detect the planet, and this shows us how exciting this field of exoplanet discovery is. Now, the music starts off quite slow, but listen to it as it gets later on. This is on the NASA Music of the Heavens webpage, if you want to look at it yourself. And the year is up on the top. Again, each ping is one planet discovered, and the total is up here at the top. The methods used for detection are shown at the top left and the top right. to 2022, over £5,000. This number has increased even more now. This video was produced in late 2022. Amazing video to see. Shows us that the next 10 years of discovering these planets is going to be an incredibly exciting time for astronomers. So, to come to the end, what has already come true? Okay, we've gone over some things that we think couldn't happen, but many things in the first Star Trek era have happened. Communicators. You all have in your pocket a device that can access the sum of human knowledge. You can also use it to look at cute pictures of cats, but you can, in theory, look at the entire sum of human knowledge. A communicator in your pocket. The US military has now developed laser systems that can detonate barrels of oil and weaponry on the opposite side of a battlefield, like a laser. Okay, just like the probes that we can see on and the weapons that we can see on some of the Star Wars and Star Trek series. Tractor beams are beams that can move objects around spacecraft. We can't do that yet on a large scale, but we can do it on an atomic scale. By using lasers, we can move individual particles around on the tiniest scale of matter. It's kind of like a tractor beam that we might find. We have universal translators, right? You don't need to stick a babblefish in your ear. You can just Google it. Okay? Google's of varying success when you translate things, but things like ChatGPT and AI are orders of magnitude better at that now already. We have cloaking devices of a varying quality. This one's a better one if you're trying to avoid detection from the military. This is the stealth bomber that can avoid being detected by enemy radar. So we can also build cloaking devices pretty easily. And tricorders. This cool invention, about a decade ago, a company built a small device that can clip into the bottom of your phone via the USB socket. It's got a small needle on the end. You stick it into your arm or somewhere. It takes a small sample of blood and does tests for some of the 10 most common diseases that were affecting people, mostly in countries like Africa where they don't have access to these facilities. And these things are cheap. You could buy one of these for about £50. And this could do blood tests and then send the information over the internet to your doctor. Incredible success. Just like not quite waving it over the dead body like we saw in the Star Trek era, but not a million miles off. Amazing that these things have now come true. And replicators. Many of you may have a 3D printer in your home. You can ask it to print you things. You can't quite yet say tea, Earl Grey, hot. But maybe that's coming. Or maybe you can. Maybe there's a coffee machine that you can... In fact, I bet there probably is a coffee machine that you can say that and it'll make the tea for you. And intelligent PCs. Many of you may also have Alexa or Google Home in your house. You can say, hey Google, what's the weather going to be tomorrow? Hey Google, what time is it? Or hey Google, which appointment have I just missed? These things are really, really cool. And they interact with all of the other websites that you use. And they look at your appointments and calendars. They can search the web for you, just like the computer could on the original series. So all of these things have come true. And perhaps the search for alien life hasn't yet come true, but maybe that will in the next 10 years. If you're curious about the correct order of awesomeness for the captains, there's the official correct order, just for information. And if you'd like to find out more about these kind of topics I've spoken about today, there's a few books I recommend. The Physics of Star Trek is quite an old book now by Lawrence Krauss, about 20 years ago. A slightly more modern one, The Physics of Star Wars by Patrick Johnson. These are both on Audible as well, you can listen to them. There's a great YouTube channel called PBS Spacetime by Matt O'Dowd. He's an Australian astrophysicist and talks about some similar things that I've spoken about today. I was lucky to give a couple of TED Talks a few years ago. I gave one about the search for alien life, called They're Almost Certainly Out There, and then one later one last year about the origin of life on Earth. And if you'd like to look at this presentation again, you can just scan that QR code. But I suppose a good way to finish is with a dreadful dad joke, which is why did Darth Vader cross the road? To get to the dark side. Thank you. Finish that. Thank you.
Thank you so much, Chris. I have to say that was, I'm sure the rest of the committee will agree with me, probably the most entertaining presentation that we've had at the university, apart from the very, very, very last bit. So, does anyone in the audience have any questions, first of all? Okay, do we have any online? Nope, okay. Right, so, yes.
I thought you'd run away there. The Alcubierre drive. The spacecraft isn't, strictly speaking, travelling, so it's not travelling faster than light. But the problem with travelling faster than light is you effectively break causality. You cause a time machine.
Yeah, it violates all the laws of physics. And strictly speaking, if you're squashing and stretching the space, the object's not moving, but it also changes the way that the light can escape from the ship. So if you're in front of the ship, of course you wouldn't see it coming until the very last minute. And the idea is that I think that when you squash the space in front of the ship, you change the way that the light moves in that section. The light still travels at the speed of light, but because you've squashed the space, the light might appear to bend. And whether or not you violate things like causality, and you can cause all these kind of weird problems with physics, you can travel back in time if you can somehow get out of it. And I think one of the big problems with the Alcubierre drive is that when you slow down and stop, the space has to then expand and the normal laws of physics have to resume. So you haven't actually gained anything by doing that. But for the moment that you were squashing and stretching the space, you could perceivably be, depending on where you're viewing it from, if you were some high-up creature, you could see the spaceship appearing to move, but you wouldn't be able to see any light coming from it. So again, it's kind of a bit of a sci-fi theory, and it violates so many laws of physics that I don't think it will ever be, well, it will definitely never be built. But more detail is contained in the Haynes manual about the Alcubierre drive, and maybe that will help with the questions.
They're managing to get taxpayers' money to fund this. Some of there are grants and things. People are putting out that they can do it more or less. There's a whole load of these ideas that people like to do research on, and they get the government, they con the government into going, hey, this isn't, because it's possible under some circumstances which aren't. Yeah, anyway, just...
Yeah, you're right. I mean, the researchers, I suppose if you're a government trying to fund research, you know, that 9 out of 10 things that you fund won't come to anything. I guess you're hoping that one out of the 100 things you put money into will become like a useful tool.
It sucks money from other physics projects.
And often it depends on who you have on the funding committees as well. Depends on who's heading up if you've got a quantum physicist on the funding committee, he tend to more likely fund those projects. So often the funding committees are thankfully run mostly by university professors. There's a few politicians on them as well, but I think they try and hire as wide a range of scientists as they can. They have like a physicist, a chemist, a biologist, an astronomer on board. So the idea is that they try and make good decisions, but I'm sure half of them are not as sensible. And you're right, if you're trying to get money out of the government, you've got to sell your project pretty well. If you know it's probably not going to work, you've got to say, well, there's a chance it could work, 1 in a million chance, but therefore it's worth the investment.
It might be possible, and so they sink money into it, yeah.
Just one other question. Talking about moving through and travelling through space faster than the speed of light, have you any ideas what effect that might have on the human body?
Well, I think as you get close, getting close to the speed of light gets very hard, and the closer you get, the more massive you become. You get this thing called relativistic mass increase, and so it takes more and more energy to get you closer and closer and closer. And anything with mass, like humans, it would take an infinite amount of energy to get something up to the speed of light, because the closer you get, the harder it gets to get even closer. Now, in theory, if you were traveling at a relatively constant speed and just getting closer to the speed of light, if you were in a well air-conditioned and well-maintained spacecraft, you probably wouldn't feel much until you got to the point where your engines were having to work so hard to keep your rocket ship propelled going forward. But you still observe things around you as normal. You still observe light from galaxies coming towards you. It wouldn't affect observations that you were going to take. But again, the chances of getting up to the speed of light is zero. So if you're traveling at the speed of light, it's anyone's guess what would happen.
Sorry. At the start, you spoke about a program you ran. It ran for 2 weeks on a supercomputer.
Yeah.
And then gave you the probability that your model of the universe was accurate.
That's right.
What was the number it gave you?
The number, of course, I wish it was 42. I really do. Unfortunately, it's not. The number I got was 0.12539. Now, of course, I remember it because I waited 6 months to see that number, and that number was the ratio of two signals in our system. So we built a model of the expanding universe, and we predicted this thing called B-mode polarization. Basically, it's like a twisting in the light that you see on the cosmic background, and the amount of twisting of the light that you get, it produces something called tensor inflation, which is a weird kind of way that the universe expands when it's very young. And so what my model did was to generate the observable signal from that weird inflation mode if our models were correct. And that was the ratio of the two, so 0.126, that was the ratio of my model to the full model. And so we could then test that against the real data and see whether that number was correct. Yeah.
Probably not a proper question, but the tattoo, the Drake term, had the term L at the end. Is that one of the originals, or is that stolen from a novel which I'm desperately trying to remember? I think it was Calculating God, where the term refers to the percentage of your population that are mad enough and able enough to get hold of nuclear weapons.
That's a great question. I'm not sure I know. I think L might be the lifetime of the species. It's a good question. I don't know the detail. I think I agree. Yeah, I agree. That's a good question. How long will humans exist for? Right? The number what do we put in for L? 1,000 years? 10,000 years? Indeed, some may say that's an optimistic number. You know, maybe we have to go to other planets to survive. Maybe all life forms eventually. I mean, imagine we did detect the signals for life, and we detected them for 100 years, and then they went silent all of a sudden. That would be even more worrying than detecting it in the first place, wouldn't it? You think, well, what happened to these poor guys? What did they do? Did their star explode? Did they bomb themselves into apocalypse? I don't know. It might be worrying, especially if we'd been transmitting signals for 95 years, and we thought, well, maybe our end is nigh too.
Would it be possible to use the interaction of antimatter and normal matter to propel a rocket in a way?
That's a great question. Yeah, great question. When you combine antimatter and normal matter, you generate so much energy. You generate this massive explosion because matter and antimatter annihilate themselves when you squeeze them together. And when you do, if you take an electron and a positron, which is the antiparticle for an electron, and you smash them together, you generate gamma rays, which are really high energy photons. Now, could you use that to power a rocket? Somehow. The gamma ray photons themselves wouldn't produce much thrust, but you could probably use that to power some other rocket system that could get us up to a higher speed. Then the problem would be, how do we make all this antimatter in space? But maybe we could develop some kind of particle collider on a ship that could produce antimatter on a big enough scale that we could then have one fuel tank of electrons and one fuel tank of protons, and then the rocket ship just combines them together, blows them up, and then we ride the shockwave. Yeah, possibly. It's a cool idea.
Good question. Just coming back to the Drake equation, which basically just takes each element of it and says, so if X percentage of that meets this this part of the equation, and then you go to X percent of that. Something that I've been saying for some time is that although we reckon we'll need a planet with a lot of surface water, wouldn't we also need a planet with a large moon? Because it's the gravity of the moon that produced the tides on Earth, which forced life from the oceans to move onto the land. And we're unlikely to have advanced life without that situation.
Yeah, it's a good question. I suppose you could definitely argue that the moon accelerated the evolution of life. I suppose for the counter argument, you could say that even with no tides, eventually the life may slowly crawl up the shore, perhaps, but it certainly would take 10 or hundreds or thousands of times longer for that to happen. I always like to remember quite how many worlds there are out there, and so and how many would have a moon like ours? Not many, you know. No. We think our moon came from the giant impact hypothesis is the most likely origin, where that's why the moon is quite a large moon compared to the Earth. And so the chance of finding that may also be maybe say 1 in 1,000, but then if you put another factor of 1 in 1,000, you still get quite a large number. But for the Drake equation, perhaps even less. You're right. So
and also, of course, the lifetime of a civilization is very important. I mean, there may be civilizations out there who are far, far more ahead of us and have the power to transmit messages at a decent rate. And suppose they've been doing so for the last 2,000 years. But because they haven't had any reply, they've decided, well, there's obviously no intelligent life on Earth, let's give up. And it's the timeline of a any advanced civilization in conjunction with the timeline of others that is going to say whether or not we can receive signals.
Yeah, it's a nice, interesting thought. And I suppose the more you think about it, the more you can start to realize that we are a relatively primordial species, right, compared to how many life forms could have evolved to a much greater extent than we have. And in a way, it's a nice validation of at least one of the rules, that we can't transmit signals faster than the speed of light. Because of all of these civilizations that have evolved far beyond us, not one of them has yet worked out how to travel faster than the speed of light. Because if they could travel back in time, and by definition, they could explore the entire universe in no time at all. Yeah. And because we've never seen them, that means that we can't. Maybe that's a law that we can't violate. Yeah. How long do we need? That's a good question.
Any other questions from the audience then? In which case, I'm sure you'd like me to tell you how much we appreciated your presentation, Chris.
Thank you.
We've all enjoyed it, but also learnt a lot from it, and we've enjoyed doing so. Can we show our appreciation, please? So, over to Alan.
Thank you, Jerry, and thank you, Chris. As I said, just a few closing announcements. I want to see you all at the AGM next week on Zoom. We've sent out details about that. Actually, we haven't sent out enough. We were going to be sending the minutes out today, but unfortunately, somebody else's computer has taken an illness which needs to be cured. So as soon as we've got those minutes available, we'll post them out along with a reminder. As I say, it's on Zoom, so we'd love to see you there. Reminder again, the week after that, we got the follow-up talk about Blinded by the Light. So we hope you'll be able to contribute to that, some of you. Our next meeting here is on June the 12th, which is really a good follow-on from the talk we've had tonight. It's talking about possibility of life on Mars, or perhaps some of the some of the moons going around Jupiter. So that one, I think, is going to be another fascinating talk as well. Please have a look at the website. It's been updated, or will be tomorrow morning, because on there is a preview of some of the talks we've got lined up ready for next year. I'm sure you're going to find that very fascinating. So, a big thank you to all of the committee, especially the technical team and everybody else who's worked in the background to make this evening possible. Thank you to everybody who was on Zoom. It's lovely to see you there. And if you are new to us, please don't go away without having said hello to us. We are a friendly bunch. We do like to meet new people as well as our familiar faces. Other than that, have a safe journey home, and we look forward to seeing you at a future meeting. Thank you and good night.
you so much. Thank you very much.